All right, this is exam 3. We will go over it. Problem number 1. We had a 0 at a pole, I'm sorry, at -2. Another one at -3. Then we had a 0 at -4. Let me move this out of the way a little bit. And then we had the root locus, which you probably could just do this on your own, right? You could figure this out on your own. I didn't even have to give you this information. But what we see is root loci start at poles and end at zeros. And they live on the real axis to the left of odd points. This is point 1, point 2, point 3. So there's nothing on the real axis that can live between point 2 and 3. So the only way to get to the 0 is to jump and has to come back on this axis, right? And then it can terminate here. But the problem is I have 2 root loci over here. And since I have to have complex conjugates, it kind of has to have the same position. And then that one heads in that direction. So that's actually all I could have done was the pole 0 map. And why am I telling you this? Because all you really needed are the poles and the zeros. So my poles, -2, -3, and my 0 is -4, and 1's at infinity. So my open loop transfer function, GH, is going to be equal to S minus the zeros all over the S minus the poles. And since I have 2 of them, that's it. That's all that you needed to do number 1. Didn't even need the root locus. You really just needed the pole 0 map. Questions on that? Because that's all you needed to do for number 1.
So that's the same as S plus 4, right?
As what?
That would be the same as S plus 4.
Yeah, because S minus a -4 is S plus 4, right? So this is equal to S plus 4 over S plus 2 times S plus 3. Right, when you cancel out the negatives. All right, number 2. So I gave you an open loop transfer function, but the next thing was, given blah, I said, find the S-plane region that results in a percent overshoot less than 25% and a 2% settling time less than 2 seconds. So, or 10 seconds, sorry. So the reality of it is, you don't even need to draw the root locus. Because all I'm looking for is the S-plane region, which means, I think my computer fell asleep again. Let's see. Sorry. We get a falling asleep computer or software. Give it a second, it usually comes back. Oh. So this is problem number 2. And so now all I really needed was the S-plane region, which is here, and it has to be in the left-hand half plane. Why can't it be in the right-hand half plane? It's even easier than that. If it's an unstable system, damping doesn't exist, right? It just blows to infinity, doesn't it? So I needed this region to calculate this angle, theta. These are the same, which we know is the inverse cosine of zeta. And then the other thing we needed was, what is my value of omega sub n? So omega sub n, if you recall, let me pick a different color. That's the hypotenuse, right? So omega sub n has to be at least as long as whatever value I need to calculate so I get my settling point, or my settling. So this here has to be at least this long. Okay. So the region is here. Now all you needed to do was calculate zeta. So zeta had to be greater than the square root. And this is the equation that we did, the maximum percent overshoot. ln of 0.25, because it's a maximum percent overshoot. So it's 25% or 0.25 divided by pi squared plus ln of 0.25 squared, which means it had to be greater than 0.404. So the cosine inverse of 0.404 is equal to your theta. What's that? Oh, yes, thank you. Got that part. And then omega sub n had to be greater than or equal to 4 over zeta times your settling time. You need me to put the numbers in there, or can you do the inverse cosine of 0.404? What's that? Omega sub n is equal to, yeah, 4 divided by 0.404 times 10. I had it 0.99, but
So I got one a day, and both because I was like, you say that the TS is equal to zeta omega sub n constant.
well, that's in the equation, right? So remember the characteristic equation is here. That's that second order system characteristic equation that we have there, right? But the settling time, remember, it has to be the settling time, so you're at least past that point. You have to be past that omega sub n value. And that is a function of zeta and omega sub n. That's why it's a curve here, not a straight line, right? So that's why I show this little dashed line like this. I don't know if you can see that's got a curve, but that's because omega sub n is the hypotenuse. A lot of people got tripped up on that one, which I was hoping not to, is really hopefully just plug and chug.
Because on the graph, it's shading, so there is minus zeta omega sub n on the right there on that point.
But here, let's bring up the slides.
Slide.
Yeah, I think it's the first or second one, we'll see. Oh, where did it go? And we even presented this.
Yeah.
We presented this, remember the class before we had the test?
Yeah.
We actually put the slide up. Shows you everything right here.
So the thing is that see what it says, second time constant is equal to omega sub n constant.
Yeah.
So I use that TS is equal to omega sub n and the doubling. Instead of
But it doesn't say equal to, it says it implies that value, right?
and then also the equation is the equation, the third order system, this is the second order system.
Why does that matter? Because a third order system has a first order and it could have a second order system. The first order system has no overshoot. Right? But the other two systems, if they are a second order system, has overshoot. So the other one is by default not going to have any overshoot because it's not on the j omega axis. It can't be. So literally, the figure that we put on the class before, it's all I was looking for. And had you given me something like this, just this figure, I probably would have given you 95% of the points you could have gotten this problem. Again, I wasn't meaning to be sneaky. It was just, do you understand? Because this is a design tool. So use it as a design tool. Questions on that? Is it quiet because you're frustrated with the test, or is it quiet because you're frustrated with yourselves that you weren't able to get that one? Or no comment? No comments fair too. All right, got to do a root locus. So our GH is equal to K over S plus 1, S plus 2, and S plus 7. So do exactly what we talked about that class before when we do the root locus. We do the poles and the zeros. So the poles are -1, -2, -7. The zeros are 3 at S equals infinity. So now we can actually start to draw our root locus by putting our poles and zeros. We have 1 at -1, 1 at -2, and 1 at -7. And now I'm going to go ahead and immediately start drawing on the real axis where my root locus exists. So it exists here, because that's to the left of an odd polar 0, and it lives over here, right? It's got to live over there, and it can't leave the j omega axis because I only have one root loci over here. Over here, I have 2. And the rule about starting at a pole and ending at a 0 immediately tells me that I have to go ahead and calculate the angles of the asymptote, the centroid of the asymptotes. And I'm leaving the j omega axis, so I have to do the breakaway points. That's the very least that I need to start to calculate. So I'm going to go ahead and solve for n minus m, which is equal to 3 minus 0 is equal to 3. So my r is plus or minus 1, plus or minus 3, and that's it. Can't go any further, right? So the first thing I'm going to do is calculate my angles of my asymptotes. So I've got 2 times, where's my equation? I didn't write it down, but it's 2 times, let's see, how do I have that? Did I keep it on here? Let me look. I just want to make sure I have the right equation. Well, I've got it in root locus. I'll just bring it up over here. All right, so it's r times 180 times n minus m, right? So r positive 1 times 180 over 3 is 60 degrees. That's the first one. The second one. And then technically, I could stop from here, right? Or we'll keep going, but you already know the next one's got to be plus or minus 180 degrees. So we're just going to check that. Minus 3, plus 3, I should say, times 180 is 180. Minus 3 times 180 over 3 is minus 180. So I have my angles, and this here checks out to what my figure looks like. I know that I have plus or minus 180, so I've done a sanity check. Yep, I'm feeling really good. Those look pretty close. So now what I need to do is calculate my location for where my asymptotes take off, or my centroids. So it's sum of the poles minus the sum of the zeros divided by 3 in this case. So the sigma of the asymptote is the sum of the poles, which we already said, -1, -2, -1. Or plus, I should say. -1 plus -2 plus -7 divided by n minus n, which is equal to 3. So that's -10/3. Which is, so somewhere over here is the centroid, right? Because we have -1, -2. And we know it goes off at +60 and -60. Now, by knowing what my angles are and recognizing that those two root loci are on the left of the j omega axis, now this tells me I need to find the j omega crossings. So I have one more thing that I need to calculate that I didn't know necessarily until I did this step. I knew I had to calculate the sigma sub b, so the only thing I need to do is a j omega crossing. So now let's calculate sigma sub b. And if you remember sigma sub b, even if you don't, let's see, where's the sigma sub b? All right, so we're going to take the partial derivative of k with respect to s, which means we take the partial derivative of -1 over gh. So we're going to take the partial derivative, sigma, of, and it's 1 over, so I have s plus 1 times s plus 2 times s plus 7. And that's going to be with respect to s, right? And I have to take the negative of that. So I'll put the negative here. So all I'm doing is taking the partial derivative of this. So let's see. That's going to be equal to negative. I'm going to move it out front. So I have 1 times s squared plus 9s plus 14 plus 1 times s squared plus 8s plus 7 plus 1 times s squared plus 3s plus plus 2. Now I sum all those terms, and I have -1. And I've got 3s squareds. I have 9, 8, 17, 20 s. And then I have 21 plus 23. I set that equal to 0 and solve for the root. So I need the roots of 3s squared plus 20s plus 23. And when I do that, I ended up with, well, let's plug in MATLAB for the roots, right? Because you all love it when I prove myself right or wrong. 3, 20, 23. All right, minus 5.19 and minus 1.48. So remember, I've got two of these. So the roots minus 5.19 and minus 1.48. Okay, so just confirm, I'm confirming. Can you tell which of those is the correct one? Is it minus 5.19 or minus 1.48?
Would be the 5.48.
Why?
Because it's between the two poles.
Yeah, you can't have a breakaway point or a break-in point unless you have a root locus, or actually two root loci that are breaking away or breaking in. So it has to be minus 1.48. Last, ooh, excuse me. Last thing we need to do is we need to do the Routh-Hurwitz. So our characteristic equation is here, right? And we only need the numerator of that. So we have 1 plus 1, or k, sorry, s plus, oh boy, this is really slow. S plus 1, and I'm going to cheat a little bit, and I'm going to combine those terms together. So I have s squared plus 9s plus 14. That's my characteristic equation is going to be the numerator. So now I have s cubed plus, and let's see, I have 1s squared, 10s squared. And then I've got to get the s terms. So I have 14 plus 9, 23, s plus 14 plus k is my characteristic equation. Let me see if I can close some stuff down. This is really bogging down here. If I clear up some memory stuff, does this help things at all? I don't want to close MATLAB. I need that. And I want to keep my PowerPoint. So I think this is the bare minimum I can have. So now I'm going to do my Ruth Hurwitz approach. S cubed, S squared, S1, S0, 1, 23, 10, 14, plus K. This is minus 1/10 times 14 plus K minus 230. And this is 0. And I'm only interested in doing the row Hurwitz up to this point because I'm trying to get the complex numbers. So I've got to make this row go to 0. So negative 1/10 times K minus 216 has to equal 0. So the negative 1/10 is gone. And what I can see is that K has to equal 216 to make that term cancel out. Questions on that? So now I'm ready to stuff that into here. So I have 10s squared. This is my auxiliary equation. Plus 14 plus 216. And then I set that equal to 0. So again, let's go ahead and solve for the roots of this equation. So I'm going to do roots of 10 and 230. Zero, yes, sorry. 0. So plus or minus 4.8. And that's where this root locus crosses that. That was the answer for number 3. Questions on that? Basically the problem we did the class before, right? Tricky, sneaky, unexpected, harder than you thought? Like that? There were a lot of struggles on this one. And you can see it's kind of a mess of how I laid it out, but it's really just the process, right? And if you looked at the handout you had, it walked you through the process to do that. You just had to be able to understand, what am I doing? All right, number 4. Come on, wake up. Number 4 is given a system, solve for steady state error. And so I'm just going to go ahead and do my open loop gain. 1 over S times JS plus B. And I'm going to put my K term over here. Now, this is for a unit ramp input. So this is when you want to go to your steady state errors and recognize for a type. Boy, oh boy. 1 system. Sorry, this is really. I don't know if I'm going to be able to do this. What is going on? I can't close Zoom. I'll have to close PowerPoint. Let's see if that helps. Does that free up any resources? It's really computers. It's on its last legs in terms of just doesn't have a lot of memory. I hate to close MATLAB. I'll close Chrome. Let's see if that helps. It is clearing up a little bit of memory. Let's give this a second just to see if it improves the performance, but whiteboard is taking up a lot of space too. I'm not sure why. I might have to clear. Just give me 1 second, see if I can clear this old stuff. Like I thought this was all on OneNote or on the Drive. I don't know how to get rid of these. Well, I don't have time to mess with it here, so I won't screw around. Like I can probably delete all these, but I don't think that that's slowing things down that much. So it's downloading it. I believe it's downloading it from the web, but it should only have this one in its memory. So, all right, so it's a type 1 system. And in a type 1 system, if you recall, my K sub V is the only term I really care about, which is equal to the limit as S approaches 0, S times my open loop transfer function, right? So that's equal to the limit. Boy, oh boy. As S approaches 0, S times K over S times JS plus B. Those terms cancel. And when I do the limit function, the J times S term goes away. So that's equal to K over B. And unless you were told otherwise, you can just assume it's a unit ramp input. So ESS is equal to 1 over K over B, which is just B over K. Questions on that? Is everybody quiet because they're confused or bored? Okay. Anybody in TV land have any questions or comments? I anticipated people struggling on the steady state errors. Anybody want to guess why? Because we did it before break, right? We started doing steady state error stuff before break, so that might have been a little bit of a gap. That's what I'm guessing. So I tried not to pick too difficult of problems, but they may still have been, I don't know. All right, last problem. So solve for K so that ESS is equal to 3 for the system that has an open loop transfer function. I'm just going to kill MATLAB and see if that helps things, because it's really very difficult to do. Let's see if there's anything else taking up a lot of resources. I'm not exactly sure what's taking up so much resources. Zoom is taking up a lot, but boy, oh boy, it wasn't a whiteboard. I have. I reset it like 2 days ago, so I don't know why it's being so funky. I'm gonna probably have to go back and delete all my old whiteboards, because you can see it's really bogging it down. So I'll do that after class and see if that speeds up things. But so my open loop transfer function is going to be equal to K over S times S plus 2 times S plus 3 times S plus 1. It's a type 1 system, so we're going to do the same thing we did before, which is given KV. So now we're going to go ahead and solve for KV. And we have the equation. It's going to be the limit as S approaches 0, S times K, S times S plus 2, S plus 3, S plus 1. The terms will cancel and the S terms go away. So what I'm left with is K over 6. And now what I said is make sure that ESS is equal to 3 or no greater than 3. So ESS, which has to be less than or equal to 3, has to be, and then that's going to be less than or equal to 1 over K over 6. So 6 over K. And when you solve for that, K has to be greater than or equal to 2. And that was it. Test number 3 in the books. Questions on test number 3? Comments? The grades on this one were a lot lower than I had anticipated. I think the average was 60 something. And I'm not sure why. Everybody speechless? How about TV land? You all speechless as well? Can you hear me?
Yeah,
I can hear you.
yeah.
Just
Yeah.
not a lot to say, I guess.
Frustrated or?
Yeah, number 2 kind of took me by surprise a little bit. I wasn't expecting settling time, so I didn't really have that at all. So I kind of made the second part of that just a guess.
Okay. That's fair. I mean, we weren't specifically testing on second order system response, but we were trying to look at, you know, where you had to do that. So again, it wasn't like hardcore root locus, but if you remember, that's when we really delved into where do we put things, because that's the only time that we varied the roots. So you could have seen, you know, a percent overshoot of whatever value, but to actually see where it is for acceptable range, that's when you color it in. That's when the root locus power really has, you know, that's where you see the power of the root locus, because then you can see points and you can pick them out. But it wasn't meant to be tricky. I think that was one of the, if you looked at the test prep, I think that's what I said, right? Based on performance specifications,
If it's a lab.
right? You had the lab that you did that. Any other thoughts or comments? How about thoughts in general? Sunny day, everybody smiling?
I think it's very good.
Yeah, everybody had plenty of time. I mean, everybody was done, I think, the last person left at 2 hours and 20 or 30 minutes. So yeah, if you want to talk more in detail about your tests, if some of these things don't make sense, let me know, we can talk about it. But if not, you want to start in a Bodhi plus today, or do you want to keep to our promise of no new material after a test?
Yeah.
Keep it out. All right, well, if there's nothing on TV land, have a great day, and I will see you all, well, some of you all in like an hour or so. Take care, everyone.
Thank you, Paul.
Thank you.